Okay, any questions, y'all, about what's coming up? Quiz on Tuesday, exam on Thursday. Exams are usually 50-ish questions. We'll take the whole class period. It probably won't take you the whole class period, but we'll take the whole class period. All right, let's see. We were dealing with forces. We did free body diagrams last time. Remember, free body diagrams are just where we describe all the forces. So, for example, in your quiz, you had a question where it asked you to find the net force on something. You had an object, and it had two forces on it, like, I don't know what it was, but 10 newtons in one direction, 3 newtons in the other direction. So that would be the free body diagram for that object. And then if we wanted to know the net force, which I think is what that question was asking, I'm sorry, that symbol is the summation symbol. It just means to add up all the forces, but we'll use net force. It means the same thing. We would say 10 minus 3 is equal to 7 newtons, and then that's our net force, adding up those vector quantities. Okay, we have some different kinds of forces, which your quiz had some things about. I think that we've already talked about weight. Right, we've already dealt with one type of force, which is called weight. Now we're going to see some other forces. For example, the normal force. The normal force arises anytime you have a contact force. It is, in fact, the equal and opposite force. When I say equal and opposite, which of the three laws? The third law, right. So Newton said that for every force that we have, there must be another force that's exactly the same, but in the opposite direction. Okay? And the normal force is that force in response to a contact force. So for example, if I have that's not a good example. For example, if I have a wall and I push on it with a certain force, say with a force of 10 newtons, so I take this wall and I push on it with a force of 10 newtons, the wall is going to push back on my hand with a force of 10 newtons. That's exactly equal, but opposite. So the wall will push back with a force that's equal, but opposite. Also, for example, if I have an object that's just sitting on the ground, and let's say that it has a mass of 700 newtons, that's the typical, or weight rather, of 700 newtons. That's the typical weight of a person, by the way, 700 newtons. That, if I draw the free body diagram, that's my weight. It points downward towards the Earth. There will be a normal force that will point upward, Fn. Here, my force weight is 700 newtons, so my normal force is also 700 newtons. A normal force, normal, means not like normal as in usual or, you know, he's not dorky, he's normal or whatever. Normal means, it's a mathematical term and it means perpendicular. Have you ever heard that term before? Normal is perpendicular. Maybe, maybe not. But that's what normal means, that normal is perpendicular. And so the normal force will always be perpendicular to the surface. This symbol means perpendicular because it's a picture, right? It's like a pictogram because these two lines are perpendicular to one another. So the normal force is always perpendicular to the surface. Notice up here that the normal force is perpendicular to the surface at an angle of 90 degrees to the surface. Over here, the normal force is perpendicular to the surface. And in fact, if I were to draw the normal force actually as it's applied, the normal force would be applied on the block from the floor like that, but always perpendicular to the surface. Similarly, if I have, say, a wall, and I'm pushing with a force here that is, say, I don't know, 30 newtons, my normal force is not going to be this. That is not my normal force. And my normal force is always perpendicular to the surface. The normal force is not necessarily in the opposite direction of the force that it's responding to. So my normal force here is always perpendicular to the surface. In that case, would that normal force be greater, the same, or less than 30 newtons? Let's do that as a clicker question. So is the normal force bigger than 30 newtons? Is it less than 30 newtons? Or is it equal to 30 newtons? Is the normal force greater than, less than, or equal to 30 newtons? I have a force that I'm pushing at an angle here, and I'm asking, this is the normal force. Is it bigger, smaller, or the same as the force that I'm pushing on? You had a question that was somewhat similar, a different situation, but somewhat similar to this on your quiz. Is it greater than 30 newtons, less than 30 newtons, or equal to 30 newtons? Again, feel free to ask your neighbor. About half the class has the correct answer. So if you ask 3 to 4 people, you should get the correct answer for one of them. And I'll stop at, say, 57. 57. Just guess if you don't know. Remember, you do get credit even if you get the answer wrong. Okay. You're pretty split. The answer is B, that it is less than 30 newtons. And this is similar to that question with the inclined plane. If you read in your chapter, there's a little section on inclined planes. And it's similar in the sense of this, that I have this object on an inclined plane, like that. The force weight pushes down, like that. And the normal force pushes up, like this. And as you increase the angle of your inclined plane, or regardless of your angle, if you have it on an inclined plane, this normal force will always be less than this weight. A quick little aside on why this is. Here, we don't get into vectors in 2 dimensions, but I can separate that force weight. It's a vector quantity. It has a direction and a magnitude. I can separate it into 2 different components. So I can separate it into a component that's in this direction and a component that's in this direction. And it's like 2 vectors that add up to give me this vector. It would be like if you were pulling on a rope in one direction, you could replace yourself with 2 people that were pulling on ropes in these directions, and you'd get the same desired effect. Okay? So the normal force here is actually going to be equal to some part of the weight, a component, or just a small part of the weight. As I make this angle bigger, and this was your quiz question, I think, right? What happens as I increase that angle? What happens to the normal force? It decreases. It gets less and less until I have the limit where I come all the way to 90 degrees, and then my normal force is what? No? It gets smaller and smaller as I increase my angle. If my angle goes all the way to 90 degrees, what is my normal force? Don't answer that yet. But think about what is the normal force. Right, if I have this pin sitting on this table, the normal force is equal to the weight. The weight points down, the normal force points up. On each of you, you have this force weight that's pulling you down towards the earth. The chair is pushing back up with that normal force. And so here I have this pin. If I increase the angle, the normal force will decrease. Now, some part of the normal force is smaller. As I increase it more and more, I'm going to hang on to it so it doesn't fall. But as I increase it more and more, to this point, what is the normal force here? What is it? 0. The normal force goes to 0 because the table's not pushing on the pin at all. In fact, if I let it go, it just falls, right? But that has to do with friction. Okay? This is a new pen, a new Nichols pen. Have y'all seen this? It's pretty nice. It's like a breast cancer awareness pen. Y'all seen these? I haven't seen those before. Okay. All right. So that's the normal force. Now let's look at friction, and we'll see some clicker questions for friction soon. The friction. Well, two types of friction. Your book didn't talk about this, but it's interesting. But I'm not going to hold you accountable for it. Did it talk about microscopic and macroscopic friction? It did. Okay. Okay. It's in the book. You're responsible for it. Okay. So friction. And I go back through the book. That's how I make the test. So if I don't know right now, I will know when I make out the test. But I usually know what's in there. I've read it many times. Okay, so friction. You have two types of friction. That's kind of cool, actually. If you didn't think the normal force was cool, which it is, this is even cooler. We have microscopic friction. And we have macroscopic. You all know what these means, right? Macro is big, micro is small. Let me explain what it means to you in terms of friction. In macroscopic friction, I have two surfaces. They come together and they experience friction just because of the big features on the surface, the macroscopic features. So I have these two surfaces, they come together, and when you try to move them with respect to one another, they bump into one another. And that is the result of macroscopic friction. Microscopic friction, on the other hand, well, let me tell you, if you take these two surfaces and you smooth them down, smoother and smoother and smoother, if I were to plot the frictional force, I'm going to plot F. This is the frictional force. We usually use a lowercase script F for friction for reasons that I don't really understand. We use a lowercase script F. That's the friction, and then this is the smoothness. So down on this end, it's really rough, and down on this end, it's really smooth. Going in that direction. Some measure of how smooth it is. As I increase the smoothness, as you might expect, the friction starts out big, and it decreases, right? You would expect that. As you make it smoother and smoother, it gets less and less frictional forces between the two objects, okay? Not smoothness. It should be smoothness. However, if you keep smoothing this, and this is a really cool thing, if you keep smoothing them over and over and over and making them smoother and smoother and smoother, eventually you get to a point where this starts to increase again. I know why that might be. The speed? No, it doesn't have to do with the speed. I mean, I'm sorry? No, not the heat. I mean, we can keep them the same temperature. It could be the heat. Like, I guess if they got hotter, the friction could increase. But it's not the heat. You keep them at the same temperature. What happens as you get objects smoother and smoother and smoother? They get closer and closer and closer, right? As you decrease these little crags and nannies and stuff in the surface, the two surfaces get closer and closer and closer. So then a couple things are happening. But the primary thing that's happening is that you have atoms in one surface and atoms in another surface, and they have charges associated with them. They're going to actually bond to one another. So you actually get friction on a microscopic level that the actual atoms or molecules will stick together. Right, so I would get, say, a positive negative molecule over here and a negative positive molecule over there, and they're going to sort of stick together. The other thing that happens is you just increase the surface area. You have more surface area touching, and so that also increases the friction. But I think this is really cool where you actually get evidence of this microscopic evidence of protons and electrons actually exist, which is not so easy to prove that they exist. I mean, we spent a long time not knowing that they existed, not until like the last 100 years. Okay? So that's friction. We have two different types of friction in practice. These are the different origins of friction. But in practice, we have two different types of friction. We have static friction. Static friction is the friction between objects not moving, or rather in contact but not moving. The static friction is like this table. If I have this table and I try to push it, I'm pushing on it with a force in this direction. So according to Newton's law, Newton's second law, that if I'm pushing in this direction with a force, it should be accelerating in that direction. Sort of. But Newton's second law says that the net force is equal to the mass times the acceleration. If I apply a net force to an object, it will cause its velocity to increase or for it to accelerate. So if I'm pushing it and it's not accelerating, what does that tell you about the net force? It's zero, right? It has to be zero. So if I'm pushing in that direction, there has to be another force that's pushing back in this direction in order to give me a net force of zero. And that force that's pushing back is what we call static friction. So here's my free body diagram. I push in this direction, but it's not moving. So that tells me that there must be another force in this direction. We're going to use our lowercase script f, and we're going to put an s for static. Now, we can calculate this Fs. It's like this. Fs is less than or equal to mu s times the normal force. Us times the normal force. So, a couple things here, several things. I'll come back to this inequality. I'll describe this in just a second. But this is called the coefficient of static friction. The coefficient of static friction is for particular surfaces. So different materials have different coefficients of static friction. For example, water or ice and steel have a particular coefficient of static friction. It's a pretty small coefficient because there's not much friction between ice and steel, which is why we use them, for ice skates or whatever. However, rubber and wood, would that have a bigger coefficient of static friction or a smaller coefficient? It would have bigger coefficient because you have more friction between rubber and wood than you do between ice and steel. So this coefficient of static friction describes the nature of the material and how they are with respect to one another. It's not for a single material either. The coefficient is always for two types of materials when they come into contact. We determine this experimentally. You just measure the static frictional force, you measure the normal force for two materials, and then you calculate what that mu should be. So it's always determined experimentally. It's less than 1. It's decimal between 0.1 and 1. So let me put that in words. This is the coefficient static friction. It's between two, describes two materials, not one material. It doesn't really make sense to talk about friction on one material. It has to be touching something. Describes two materials and how they come into contact. It's less than 1. Has no units. You could do our little dimensional analysis, right? We know that the units of the normal force are in newtons. The units of the static friction are also in newtons. So therefore, mu doesn't have any units at all, right? Because I don't need anything here in order to give me newtons on both sides. I already have newtons. Okay, now let's talk about this inequality right here. So, I push on this table with 2 newtons. Right now I'm pushing with 2 newtons, like a half a pound of force. What is the static frictional force? Is it equal to 2 newtons, greater than 2 newtons, or less than 2 newtons? Equal, greater, or less? I push on this table with a force of 2 newtons in this direction. You see me? I push on with 2 newtons. What is the magnitude of the static frictional force? Is it equal to 2, greater than 2, or less than 2? Go ahead and put in your answer. A equal, B greater, C less than 2 newtons, as I'm pushing on it with a force of 2 newtons. Okay, all right, getting it. So remember Newton's second law. Newton's second law says that the net force is equal to the mass times the acceleration. So if I have a net force, that means the velocity must be increasing in some way, or must be changing, because the acceleration describes how the velocity changes. And if I have a net force that's bigger than 0 or not 0, then my velocity has to be changing in some way. If I push on this object with a force of 2 newtons, is its velocity changing, or is it staying exactly the same as it is? It's staying exactly the same, right? It's not moving. And further, it's not accelerating, right? So it's stationary, the velocity is not changing. So that tells me that the net force on this object has to be what? It has to be 0, because it's not moving. So Newton would say, well, the net force has to be 0 because it's not moving. All right? Okay, that didn't help very much. So if my net force is 0, that means that the sum of all the forces is what? The net force is what? Right. So the sum of all the forces, the vector sum, the forces in one direction, the forces in one direction, they have to come together to give me 0 force. Ask your neighbor what they put, okay? A lot of you have the wrong answer. Ask your neighbor what they put and think about that. I'm asking, what is the static frictional force on that table if I'm pushing on it with 2 newtons? Okay, we're a little better now. Y'all have, everybody has either A or C, and you're about evenly split between A and C. And one of those is the right answer, between A and C. Somebody might have put B since then. Okay, it's not moving, so that tells me the net force is equal to 0. Okay, let's go ahead and see what we got. Okay, I'm going to stop here. It's pretty important. Let's try it again. Okay, but I'm going to ask you now not about the table. I'm just going to draw the picture up here, right? I've already drawn the picture. This is equal to 2 newtons. I know that the net force is equal to 0. So what must this force be? What must the magnitude of that force be? Go ahead and put in your answers. This is the same situation. I'm pushing in this direction with 2 newtons. There's a static frictional force in this direction. I want to know, what is that static frictional force if it's not moving, if it's not accelerating? Okay, that's a lot better. I'm going to stop at 30. I don't think you get a joke for that because I so led you into that answer. Should you get a joke? What happened? Oh, I'm sorry. I'll give you a joke since we lost those points. I don't think we lost them. We might not have. Yeah, I guess so. All right, y'all do it in again. Put your answer for that last one again quickly. All right, I'll stop at 12. He is right. Awesome. Okay, the net force is 0. I think that this is exactly the same as the table. Force pushing in this direction, static frictional force in that direction, net force is 0, so these two have to be the same. But a lot of you said that the static frictional force has to be less than 2 newtons, right? You said this was the answer, right? Half of you said this was the answer before we did that. But if that were the case, if the static frictional force were less than 2 newtons, let's say that the push was 2 newtons and the static frictional force was 1 newton, gosh, what's going to happen to that table? It's going to move, right? And in fact, that's not static friction when it starts moving. That's something called kinetic friction. Okay? What's the worst thing about living on O Street? You have to walk a whole block to pee. Is that vulgar? That's not vulgar, is it? That's like a 7-year-old joke, okay? What's the worst part about living on O Street? You have to walk a whole block to pee, like O-P Street. Yeah. Okay, so that's our static friction. Now, back. That inequality. I push on this with 1 newton of force, a quarter pound of force. A newton is about a quarter pound. So if you ever go to McDonald's, you can admit it if you go to McDonald's, it's okay. All right, quarter pounder with cheese. You should ask them next time you go there, if you get the quarter pounder with cheese, say, hey, I want a newton with cheese. Because it's the same. It's about the same. It's about a quarter pound. What was I saying? Oh, I'm pushing with a newton, about a quarter pound of force in this direction. It's not moving. So I say, well, I'm going to push with more force. I'm going to push with a half a newton. It's not moving. When I'm pushing with 1 newton, I'm sorry, I push with 1 newton, it's not moving. Now I'm pushing more with 2 newtons, it's not moving. 3 newtons, it's not moving. When I push with 1 newton, what is the static frictional force? It's 1. When I push with 2 newtons, what is the static frictional force? It's 2. When I push with 3, it's 3. Okay, so the static frictional force is always in response to another force. Let me draw that picture, just to make sure that you're clear on that. If I have a force equal to 2 newtons, my static frictional force is 2 newtons. If I have a force with 3 newtons, my static frictional force is 3 newtons, and on, until the object moves, and then static frictional force doesn't apply anymore. So that's where that less than or equal to comes from. That there is some maximum static frictional force between two surfaces. That maximum is equal to this. The static frictional force is always going to be less than or equal to that maximum. If ever you exceed that maximum, the object is going to move, because then your frictional force isn't enough to hold it in place. So this represents the maximum static frictional force. Okay? Now, when the object starts moving, one other thing I want to tell you. So this is mu s, and then also the static frictional force is dependent upon the normal force. You can take a pen or a pencil or whatever, like this on your table. Take your pen. You can push down on it. And when I push down on this thing, what am I doing to the normal force? It's increasing, right? If I draw the free body diagram for that, here's my object. There are some forces acting on it, the weight. And then if I push down on it, I'll call that just F. If I push down on it, then that's also going to add to that. My normal force then will equal F plus the weight. So if I have my pen here, and I just push down lightly, and then I try to pull it across the desk, I'll try this. Pen on the desk, push lightly, and then pull it across the desk. You can feel the friction, right? The surfaces rubbing against one another. And now push down harder and try to move the pin. Can't do it. You'll do it? Because what you're doing there is you're increasing that normal force. Sorry, here, you can be the proud owner of a nickel steak. You got it? Okay. She broke her pin. Huh? It's a nice one. The first person to race up here after class. You want it? Yeah. Okay, so what was I saying? So if our normal force increases, the static friction increases as well. Del? Yeah, there could be. I mean, like, for example, if I have my pin, if I push on this wall on the pin, then it increases the normal force on the pin and increases the static friction. So when I'm pushing on this, the force that's holding the pin up is the static friction, not my finger. My finger's not holding it up. Right? It's the static friction. And if I decrease this, I'm still touching it, but eventually the normal force decreases and the static friction decreases. Similar with the belt, right? The belt is like one of the most ridiculous things that we ever have created, right? You aware of this? I'm trying to get my wife to put buttons on all my pants so I can wear suspenders. Because that makes a lot more sense. What you're doing is you're using a belt. You increase the normal force on your waist to increase the friction to hold up your pants. And that's kind of ridiculous. Because you got to cinch it down pretty tight to increase that static friction enough to hold your pants up. So suspenders make a lot more sense because they exert a force that's up, which is exactly opposite the force of the weight of the pants, which go down, which is not where you want your pants to go. Okay, does that make a little bit of sense? Yeah, so you can have a frictional force that's pushing on a vertical surface, like your waist or the board or whatever. She says that I would look dorky in suspenders. Harley? If the object is not moving, the net force will be zero, in which case the static friction will always be equal to the opposing force. Yes, that's true. Okay? All right. Well, let's go back to the inclined plane, too. So as I have my inclined plane, we talked about this, as I increase the angle, the normal force decreases. What happens to the static frictional force that holds whatever it is on the inclined plane? What happens to Fs? Up, down, stay the same? It goes down, right? So when I have, that's a little nasty, right? If I increase my angle, what causes it to go down is the static frictional force decreases enough. The normal force decreases enough so that the static frictional force decreases and the thing slides off. All right. Okay. Kinetic friction is a lot simpler, and it's a lot similar too. Kinetic friction, we'll call it Fk. K is for really cool. Now K is for kinetic. Call it Fk, and it's equal to mu k times the normal force. So it's exactly like the static frictional force, except now instead of mu s, like we had before, we have mu k, and then we also don't have that funky inequality sign. We just have an equal. Typically, with kinetic friction, regardless of your speed, to within certain limits. If you go really fast, then you can heat up the surfaces, and that changes the friction. But typically for kinetic friction, it's always it remains constant, so we just use the equal sign, and it's mu times the normal force. Mu times the normal force. An interesting thing, something you can test when you leave here this afternoon or this morning, is that mu s is almost always bigger than mu k. I think it's always bigger, actually. I'm not sure it's ever less. So for example, a good a good place that you might have seen this, if you have like a heavy piece of furniture or something, and you're pushing it across the floor, it takes a big strain to get it started, but once you get started, it's really easy. And that's because kinetic friction is always smaller than static friction, because this relationship between the coefficients. By the way, it looks like an M. It's the Greek letter mu. It's a U with an extra little tail on the side. All right, so the mu for S is bigger than mu K. You can see this too. This is kind of cool. You should tell your friends about this. You know this stop sign out on the end of Maidwood as you're zooming up out of campus and you come to that stop sign right in front of Highway 1? I know that y'all don't usually stop at that stop sign, but today as you come up to it, I want you to come to a very slow stop. Okay? Okay, y'all probably stop there because you're very responsible, right? So come to a very slow stop. You don't have to do a real slow stop, but your friend, if he or she is sitting next to you, say, "Hey, watch what happens," and slow down, and slow down, and slow down, and right before you come to a stop, what's going to happen to your car? Y'all don't stop at that stop sign. Your car's right, yeah. Emily, right? So she stops. I know. It's going to lurch forward just a little bit. You're just going to feel a little hitch. And the reason that is because, you know, your brakes, they have this metal disc. They have these clamps, these brake pads that clamp down onto that metal disc. And they're clamping down while your car is moving. What type of friction is that? The friction between the brake pads and the rotor. That's kinetic friction, right? Because the rotor's moving with respect to the brake pads. That's kinetic friction. And then your car is going slowly, 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 coming to a stop. And you have this transition between kinetic friction and static friction. Because they're different, static and kinetic friction, that's why your car sort of lurches forward a little bit. Okay, y'all try that and tell your friend. They're going to be, wow. They're just going to say, gosh, you are like the coolest person that I've ever met. They are. And you say, I'm just normal. That is perpendicular to the chair. Okay? Because modesty always works well with those sort of compliments. All right. Okay, free body diagrams. Let's do a few clicker questions. Did these. What's that? No. When we're done with this, by the way, I'll post it online. And that'll be another place for you to look to sort of practice. And I'll pull a few questions from this too, either very similar or maybe verbatim for the test. So get that one. Okay, we're still on Newton's laws a little bit, so let's do this one. Very large truck sits on a frozen lake. Assume there's no friction at all. Now, that's not really true for a very large truck on a frozen lake, but let's assume that there's no friction at all between the tires and the ice. A fly smashes into the windshield. What happens to the truck? Does it just sit there because it has so much inertia? Does it move backward at a constant speed? Does it accelerate backward? Does it move forward at a constant speed? Or does it accelerate forward? This is all in the instance that the bug smashes into the windshield of the truck. And you can ask your neighbors. Think about what's happening. And remember, no friction at all. That's not very realistic. So, but no friction at all. So we might want to second guess yourself. I think 5 of you have the right answer right now. So, um, all right, we'll stop it. 145, 145. I'm sorry, did you not get in? Okay, it's not a big deal. All right, so most of you did put A, but the answer is, what do y'all think? Okay, it accelerates backwards. A couple things that come into play here, right? We'll think Newton's first, second, and third laws, they all come to play. All right, so the fly comes along and smashes into the truck, and it gives a force on the truck. Or rather, the truck pushes on the fly, pushes it and all that. But as a result, you also have a force pushing on the truck. It's a small force. Yeah, it's a small force. But nonetheless, you have a force that's pushing on the truck. Okay, there's no friction, so what's going to happen to that truck? It's going to move. It's going to accelerate, in fact, in that moment that the bug is smashing into the window of the truck. Because I have the front window. But if it was the back window, that wouldn't really change things. I'm sorry? No, it was just sitting there. Okay. So it's going to cause it to accelerate backwards. Now, a lot of you put A because it has inertia, right? And that's true. It does have inertia. Just a second, Emily. So it does have inertia. That just means that it's not going to accelerate that quickly. But when I have this force that's pushing on it, and the net force is bigger than 0, then it must accelerate. That's what Newton's second law says. Emily? That's right. So it would accelerate up to a certain point while the bug is smashing into the window. And then after that, it would travel at a constant speed forever. B is sort of right, and B is sort of like the next best right answer. But I did say in the moments that the bug is smashing into the window. That's when the force is being applied. And then once you take that force away, after the bug is smashed into the window, then you're right, Emily, that it's going to move backward at a constant speed, whatever that speed it accelerated up to. It has to, because it was at 0. Right. Because at 0, it moves up to a constant speed while the bug is smashing into the window, and then it travels at that speed forever, or until a force acts on it. Okay? Oh, I'm sorry. So this isn't right. It accelerates backwards because you're looking at the moment when it smashes in. You follow? It's C, right? It is C. Well, it depends. If you're looking at it in the moment that the bug is smashing, which is what I said, or after that, as Emily pointed out. Okay, what can you say about the force of gravity acting on a stone and on a feather? I call this FG here, but we've called it FW. It's the weight. What is the difference between stone and a feather? Don't try to overthink it too much. All right, I'll stop at 55, 55. Let's guess if you're not sure. Yeah, stone and a feather. The stone is typically heavier than the feather, right? That makes sense. The stone, it has more mass, so it also has a greater weight. Okay. Um, what can you say about the acceleration of gravity acting on the stone and the feather? I don't remember if we actually talked about this. Did we talk about this? Huh? What is the acceleration of gravity acting on the stone and the feather? Go ahead and put what you think, and then before I turn it off, we'll talk about it. I'll let you get the right answer. Okay? A lot of you have your answers in. I'm going to keep it going. I'm going to show you the answer. Uh, I know from Newton's second law that F is equal to m times a. And so when I'm talking about the force weight is equal to m times what we call the acceleration due to gravity, or g. So this is just a particular value for the acceleration due to gravity. And anytime I want to calculate the weight, I just multiply my mass times this. So, you know, if I'm 70 kilograms, which I am roughly, I multiply that times 10, which is g, and I get my weight, which is 700 newtons. That's like the difference between a slug and a pound. Okay, the difference between mass and weight. And so the acceleration due to gravity on the planet Earth is always the same. It doesn't matter if you're 70 kilograms or 150 kilograms or whatever, that it's always going to be the same. And so here the answer to this is it's equal on both always. Okay? But then you ask, well, if I have a stone and a feather, we'll let this be our stone and let this be the feather. This is heavier than this, as you might imagine. If I let them go, which one's going to hit the ground first? The marker, right? The stone will hit the ground first, right? And so that doesn't make any sense, because we just said that the acceleration due to gravity, the amount that its velocity increases with time, meters per second squared, is the same for both of them. So why do they fall at different rates? If I just said that the acceleration is the same, why do they fall at different rates? Because of what, Ellen? No, it's not their mass. Air resistance. So this is a big flat surface. This is a not flat surface. And even though this is heavier, it falls faster not because it's heavier, but because it doesn't have as much air resistance as this. So if you imagine in your mind drawing your free body diagram on this sheet of paper, you have one vector that comes down, that's the weight, and then you have another vector that comes up, that's the air resistance. It's sort of like the friction in the sky, okay? And it's going to slow it down and give it a lesser acceleration, give it a lesser net force. Now, we can do a couple of things. Is this somebody's? This is yours? Can I use one of your notebooks? I won't hurt it, I promise. Now, look, I can get rid of that acceleration. I can get rid of that air resistance. Watch this. If I drop these, same thing's going to happen. That falls a lot faster. Watch this. If I put this on top of it, then there's no air flying against the sheet of paper. It's not connected to the notebook, but watch what happens. Oh, that's pretty cool, right? So it accelerated at the same rate as did the big old thing because there was no air resistance. You can do that with a feather, too. Like, you have a feather, you can just put it on top of the notebook. Or you can do this, right? I have these two. I can get rid of a lot of the air resistance just by crumpling it up. They fall at the same rate. Their masses are still the same. I'm just changing the friction in the sky, the air resistance. Okay, a few more minutes. Okay, so the answer here was D. I'm going to stop just a couple seconds. All right. I'll put these. Okay, this is kind of cool. A block of mass m rests on the floor of an elevator that is moving upward at constant speed, not accelerating. Acceleration is 0. It's moving at a constant speed. What is the relationship between the force due to gravity, or the weight, which is mg, and the normal force? Is the normal force bigger than the weight, equal to the weight, less than the weight, or equal to 0? Or does it depend on the size of the elevator? Think about my force diagram. What are the forces acting on it? I only have a couple of forces. What is the acceleration? Is it 0 or not 0? What is the net force, which is related to the acceleration? And then, how do those two forces, the weight and the normal force, compare? Just a few more seconds. I'll stop at, say, 128. 128. Just guess if you're not sure. Oh, awesome. Yeah, pretty good job on that. All right, so B is the right answer. The normal force will equal to the weight. And so this is exactly the same as if it weren't moving at all. It says it's moving at a constant speed, but that means the acceleration is equal to 0. That would be exactly the same as if the object was just sitting somewhere not moving at all. Another question related to this. A block of mass m now is accelerating upward in an elevator. What is the relationship between the force due to gravity and the normal force on the block? I'm going to help you a little bit. I'm going to draw my force diagram over here. This is my block. I have the normal force going in that direction. I have my weight going in this direction. I've told you that it's accelerating in the positive direction. So my acceleration is positive, bigger than 0. And I want to know how is the normal force related to the weight. And remember, my net force is equal to mass times acceleration. So what happens to my normal force versus the weight when I accelerate upward? It has to be different from the previous question, right? Because the previous question, it had 0 acceleration, and the normal force was equal to the weight. Now, what's going to be our answer here? Will it be greater than the weight, less than the weight, or 0, my normal force? It's got to be either A, C, or D. Which is it going to be? All right, I'll stop at 145. 145. Oh, you are awesome. Got it. A is right. That my normal force is bigger than my weight. This is why when you go into an elevator, you sort of feel like you're being pulled down. All right, the reason for that is that, well, you're accelerating upward. But if you were actually standing on a bathroom scale, the bathroom scale does not measure weight. The bathroom scale measures normal force. It measures what is the equal and opposite force that is opposite your weight. And that force is the force that the scale pushes back up on you. That is the normal force. So if you took a bathroom scale into an elevator that was accelerating upward, like a really big elevator, like, I don't know, in New Orleans or wherever, you can't find one in Thibodeau, but your weight on the scale would appear bigger because the normal force would be bigger. So I can think about this in terms of my force diagram. I say that my net force is my normal force minus my weight, and that's equal to the mass times the acceleration. And so my normal force is equal then to ma, that's my mass times acceleration, plus weight. So my normal force is equal to the weight plus this extra thing, which arises out of Newton's second law. My normal force is bigger than the weight. Now let's do one more, and I think we'll make this the last one for today. Oh, we've already had this question, so this one should be easy. And then I want to tell you one thing before you leave. Which of these is the normal force greater? A, B, or do they have the same, which is equal to the weight, same, which is greater than 0 but less than the weight, or same but equal to 0? All right, just a few more seconds. I'll stop at 50. And don't leave yet. I want to tell you something. So stop at 50. Okay, that was pretty good. A is the right answer. the normal force is greater. As you increase that angle theta, the normal force decreases. That was on your reading quiz. Listen, folks, I know that this first chapter doesn't seem real applicable to what y'all do, but we're about to get into stuff with muscles and torques and stuff like that. And that for you athletic training majors, it is more applicable. And then later chapters are more sort of geared towards the human body. Just want to make sure that you're not discouraged. All this Newton law stuff, like it gets a little bogged down. And then also don't forget, quiz on Tuesday, test on Thursday. So be preparing now. Don't wait until the last minute. Have a great day.